Thanks everyone for joining. Our presentation today will start with central plant improvements. These types of projects typically require significant amount of capital investment and should be considered when the existing central plant equipment is scheduled for replacement. After central plant improvements, I'll be talking about ventilation and lighting system improvements as well as energy efficiency projects. Lastly, Todd will be speaking about funding impact for these types of energy efficiency improvement projects. So let's start with central heating and domestic hot water heating plants. Central heating plants typically produce hot water or steam for space heating using hot water boilers or steam boilers. Central domestic hot water plants produce hot water for the building's plumbing fixtures, on the other hand, and these central plant projects, as I mentioned earlier, are more suitable for older buildings where aging central plants require replacement. When central heating or domestic hot water plants are scheduled for replacement with higher efficiency equipment should be considered. Common options here include higher efficiency condensing boilers, hybrid boiler plants with non-condensing and non-condensing plants, and also steam to hot water conversion. I won't be getting too much into technical details, but these are basically types of systems that can potentially provide higher energy efficiency. And with these types of projects, we typically see 10 to 20% energy consumption reduction with 1 to 7 years differential payback when compared to replacement with standard efficiency equipment. I think the term differential payback is important here because as an association, when equipment needs replacement, there's really no do-nothing option here. And as I mentioned earlier, when the equipment is scheduled for replacement, consideration should be given to installation of the higher efficiency equipment because usually the premium is minimal. So for these types of projects, planning and phasing is critical for successful implementation. Please also note that when this type of equipment is replaced, we should always think about, in addition to energy efficiency, we should always think about improving redundancy, comfort, and reducing maintenance expenses as well. It is also important to note that there are additional creative options that can be investigated at this phase. These can include fuel switching if there is conventional electric heating equipment. For instance, this would include switching from electric heating to natural gas heating. Just an example, in order to produce same amount of energy to provide heating or cooling, using electricity is almost 3 times more expensive than natural gas if a conventional electric heating equipment is being used. That doesn't mean all electric equipment is costly. There are energy efficient systems such as VRF systems, which I'll mention. Other than that, so microturbines for combined heat and power generation and solar thermal domestic hot water heating are also creative, energy efficient, sustainable options. Those should be looked into if it's the right application for your building. Also, as I mentioned, variable refrigerant flow systems, what we call VRF systems, these are becoming more and more common. These systems basically use electricity and use refrigerant as a heat transfer medium and provide higher air conditioning and heating efficiency for your building. That would need to be looked into and investigated to determine if it's the right application for your building as well. So moving to central cooling plants, chiller plants. So like central heating plants, central chiller plants produce chilled water for space cooling instead of hot water. These systems produce chilled water. And central chiller plants in residential high-rise buildings typically consist of water-cooled or air-cooled chillers. If there's a water-cooled chiller, that means a cooling tower is also required to provide heat rejection for the water-cooled chiller system. Air-cooled chillers, those systems do not require cooling towers as they directly reject heat to the atmosphere. For central chiller plants, higher efficiency options include variable speed chillers, chillers with magnetic bearing compressors, and with these types of projects, we typically see 10 to 40% energy consumption reduction with 1 to 5 years differential payback when compared to replacements with standard efficiency equipment. Again, in addition to energy savings, there would be additional benefits related to equipment operation, maintenance, and redundancy. So as mentioned earlier, those projects I mentioned in the previous two slides usually require significant capital investment, and they should be considered when the existing equipment is scheduled for replacement. However, not all energy efficiency improvement projects require high capital investments. Two types of projects, for instance, here in the slides, require lower capital investment and are not large construction disturbance usually. As mentioned earlier, water-cooled central cooling plants use a cooling tower to reject heat absorbed during the air conditioning process. From energy efficiency perspective, one low-hanging fruit for cooling towers is basically installing a variable frequency drives or VFDs on cooling tower fans. This is a very simple project. The goal here is to provide capacity control for the heat rejection system to minimize fan energy consumption during low load conditions. These types of projects typically result in 40 to 60% energy reduction on the cooling tower fan, which is very significant. The second consideration for central cooling plants is installation of water-side economizers for what we call free winter cooling if air conditioning is required during winter time. So this doesn't apply to all building types, but some buildings, what we have seen historically is usually higher end buildings, are designed with what we call four-pipe distribution system, which means that both hot water and chilled water is available at the same time for space conditioning. These buildings typically are designed to provide air conditioning even during winter time as well. Year-round cooling is available in these types of buildings. Please note that not all buildings have four-pipe system. Having a two-pipe system is more common application for high-rise condominium buildings. But if your building has a four-pipe distribution system and requires air conditioning during winter time as well, what we suggest is basically installing a water-side economizer, and that can provide free cooling for the building using environmental conditions when it is cool outside. So instead of using the electrical energy to provide air conditioning, it would utilize the environmental conditions, the cold air outside, to provide air conditioning for the spaces. Okay, I will move on to building automation system. I think most of you are familiar with the term building automation system or energy management system. So building automation systems provide centralized control of buildings' HVAC systems. They can even be extended to include security and other types of building systems. There's usually a misconception that the building automation systems require too much capital investment. That depends on how we approach to this project. It is not the case usually, as the project can be implemented in a phased strategy. Building automation system integration is flexible, and depending on your association's budget, it can be implemented in phases. It allows equipment and monitoring capabilities to be added throughout the life of the building. This flexibility would allow the building to only add the most sensitive HVAC equipment initially and continually add equipment as the association's funding allows later. With implementation of energy efficient control strategies with building automation systems, we would typically expect 5 to 50% overall building's energy consumption reduction, which is significant. So another energy efficiency measure that requires lower capital investment and is not a large construction disturbance is installation of VFDs on buildings' hot water and chilled water pumps. So typically, high-rise residential multifamily buildings have chilled water and hot water distribution pumps that distribute space conditioning water from the central plants. And typically, what we see is these pumps operate at constant speed, regardless of how much cooling or heating needed at the building. So the goal by installing variable frequency drives here is to minimize pumping energy during low load conditions by installing VFDs. So for instance, when it's really not very hot outside during shoulder months, those pumps doesn't need to run as hard as when it's really warm outside. So it'll be important to take advantage of that low load conditions to save energy. And with these types of upgrades, we would typically see 40 to 60% pump energy consumption reduction. So the next item would be ventilation system improvements. In high-rise residential buildings, exhaust is provided by central kitchen, dryer, and toilet exhaust fans, and while fresh air is provided by central makeup air unit. So when we think about ventilation system in high-rise residential buildings, we need to think about exhaust and makeup air units. So the exhaust air from residential kitchens, bathrooms, and dryers are typically replaced with conditioned, filtered outdoor air provided by central makeup air units. When it comes to building central ventilation system, there are several projects that should be considered not only to increase energy efficiency, but also to increase building pressurization, comfort, and some issues resulting from stack effect because we have a high-rise building. So one of the potential projects I'd like to talk about is exhaust heat recovery. With exhaust heat recovery system, energy recovered from the building's exhaust systems would be used to preheat or pre-cool the makeup air to reduce load on the building's central heating and cooling system. Energy savings and return on investment on these types of projects are highly dependent on existing equipment location, capacity, and design parameters. So a detailed analysis, engineering analysis, would need to be performed to evaluate feasibility of these systems. The second item I would like to talk about ventilation is energy efficient summer dehumidification. So dehumidification is critical, and not all central makeup air units are designed to provide summer dehumidification. I think back in 60s and 70s, dehumidification was not considered to be a critical feature for building ventilation systems. So when summer dehumidification is considered, heat recovery systems can be utilized to avoid or minimize additional energy required for the dehumidification process, because there's a difference between a regular cooling process and dehumidification process, and dehumidification process requires significantly more energy. And this type of upgrade should be considered when the existing makeup air unit is scheduled for replacement as well, just to make it cost effective. So the next topic I'd like to talk about under ventilation systems improvement is also a very important one. It's demand control ventilation for residential spaces. So for residential spaces, another ventilation system upgrade that can significantly reduce energy consumption is implementation of demand control ventilation. So as I mentioned earlier, typically exhaust is provided by central kitchen, dryer, and toilet exhaust fans, while fresh air is provided by central makeup air units. So typically these systems operate at constant speed, regardless of building's real-time ventilation needs. By installing variable frequency drives and upgrading controls associated with these systems, the goal here is to minimize overall ventilation load in residential spaces when certain spaces are not utilized. For instance, when most bathrooms and kitchens are not utilized at 3 a.m. in the morning in a building, the central exhaust fan serving these spaces can slow down and save energy, and that is a significant amount of energy. Please note these projects may require some condo zone level upgrades. These are typically minor upgrades, such as installation of automatic control dampers or switches in the kitchens, bathrooms. And with demand control ventilation in residential portion of the building, we typically see 40 to 60% fan energy consumption and 20 to 30% heating and cooling energy consumption reduction. So the main benefit of demand control ventilation is that not only we are achieving fan energy savings, but we are also achieving heating and cooling energy consumption savings, which is very critical, because if we are controlling the speed of the exhaust fans, that means we are controlling the amount of air being exhausted, removed from the building. That means we need to bring less fresh air to the building, and we need to air condition less air introduced to the building. So that's a significant part of this project. So demand control ventilation for garage areas, this is a very similar concept. The goal here is to reduce ventilation load in enclosed garage spaces based on real-time activity in the garage. Energy savings associated with these systems is more significant if the building has a heated garage, enclosed garage. The system would basically utilize carbon monoxide sensors and detectors to track garage activity, and equipment providing ventilation for the garage space would be controlled accordingly to save energy. With these types of upgrades, similar energy savings would be expected, 40 to 60% fan energy consumption, depending on system details, and 20 to 30% heating energy consumption reduction. So with ventilation systems out of the way, I would like to talk about lighting system improvements. I'm sure most of you heard about LED lighting and how efficient they are. So yes, typically lighting system improvements include installation of LED lights as well as smart lighting controls. The main benefit of LED lighting is that today's LED lighting technology uses approximately 75% less energy and lasts 20 times longer than traditional incandescent lighting. So I know incandescent lighting is not that common these days. So compared to LED to incandescent lighting may not be that that feasible. But the table on this slide also provides a comparison of LED and fluorescent lighting to traditional light bulbs, as well as the difference between LEDs and fluorescent lighting as well. So you can see on this table that even though the energy performance of today's fluorescent lighting is somewhat close to LED lighting, the expected service life of LED lighting is more than twice than fluorescent lighting. So that should be taken into consideration as well. And in terms of lighting controls, we recommend using dimmers, motion, and occupancy sensors and timers. And again, here the goal is to use these controls to turn lights on and off as needed to save energy. So lastly, before handing this over to Todd, I would like to talk about energy efficiency incentives. And before getting into details of incentives, I'd like to talk about where these incentives are coming from. The utility companies usually charge their customers with an energy efficiency charge as a percentage of the overall consumption amounts. So if you check your utility bill, whether it's a common building meter or a residential meter, you will see an energy efficiency charge from your utility company. And these charges are basically collected by utilities to promote and fund energy efficiency upgrades, and is returned back to the customers through these energy efficiency measures, programs, services, and incentive programs. So please note, almost all energy efficiency improvement projects qualify for incentives via local utility programs. Typically, there are two types of incentives. There are prescriptive incentives, and these incentives are based on specific dollar amounts for completing qualifying energy efficiency measures. For instance, if you're using a smart thermostat for your home or for your building, the prescriptive incentive is based on X amounts of dollars per thermostat. And the second type of incentives are custom incentives. And these incentives basically, if there's energy savings involved, if it's not qualifying for prescriptive incentives, it'll be qualifying for custom incentives. And these custom incentives are based on basically dollar per electricity or natural gas saved. So typically these types of incentives require more analysis and detailed energy saving calculations. And whenever we are implementing energy efficiency improvement projects, we also manage incentive applications for our clients as Elara. We have obtained over $6 million in incentive funding for our customers. You can also check our website for successfully completed energy efficiency and improvement projects for high-rise buildings, and most of these projects include significant incentive amounts successfully procured for our clients. With incentives out of the way, I'll hand over to Todd, and he'll be talking about funding impact for these types of projects.
Well, thank you, Sam, and good afternoon, everyone. I'd appreciate the next few minutes to discuss how these energy efficiency improvements impact the ability of associations to fund their capital-intensive replacement projects. The following illustrate various funding scenarios based on replacement options for building heat and domestic hot water boiler systems. The first scenario includes replacement with limited improvements at a lower initial capital investment, while the second scenario includes replacement with significant energy efficiency improvements and thus at a higher initial capital investment. It's important to note as we go through these scenarios that the options, the costs, the reserve funding, and especially the energy savings are going to vary greatly based on the specifics of your property. The first scenario assumes replacement with minimal or limited system upgrades. Of course, the association will gain some efficiency improvements simply due to improvements in technology and boiler systems. The old vintage boiler systems, it's not possible to replace in like kind. So you will get some efficiency improvements just naturally through those technology improvements. In this scenario, the boiler replacement expenditure is noted in 2022, so in the near term, as just over $600,000 and highlighted by the red box. Now, I recognize that there are a lot of numbers on this page, but the focus is really only on 4 locations. It's important to note that these scenarios assume that the association will utilize natural gas cost savings from energy efficiency improvements to fund reserves and future capital projects. Maybe this association has some big projects coming up that they're worried about how they're going to fund in addition to this boiler project. So we're assuming for purposes of this analysis that they're taking those energy efficiency savings and putting them towards reserves. Associations, of course, could use the savings to offset operating budget expenses. You can see these savings highlighted in the row with the red box. The blue box in 2022 includes the boiler project among other expenditures. So that's where that $600,000 boiler project is located on the expenditure side, is in that blue box. In these scenarios, the low point in the cash flow analysis, or the minimum threshold, is 2030. So all funding plans go through that low point, that minimum threshold point of 2030. So the benefit of this scenario is a lower initial capital cost. However, note the limited annual energy cost savings that are going towards reserves, just $10,000 annually. Finally, as we go through these scenarios, note the overall amount being contributed to reserves over time. In this case, in 2030, over time, $775,000 total being contributed to reserves, with the vast majority of that, $765,000, coming from owner assessments and very little from energy cost savings. Now let's assume now that a scope of work that includes significant energy efficiency improvements. And you can note the significantly higher cost for the boiler project in 2022, now at over $1 million. So the benefit of this scenario is obviously much greater annual cost savings through the energy efficiency improvements. It's a much larger amount, $80,000 annually. And so you can see that over time, the significant utility savings result in a greater amount of total funds being accumulated towards future capital projects and future capital repairs and replacements, while at the same time a reduction in the amount of the contribution coming from annual owner fees. Again, away from investment and significant energy savings is over time, and I have to stress that over time part, a higher overall contribution in 2030 with a lower amount coming from annual owner fees. The final scenario assumes use of a loan to fund the initial investment capital project, the capital intensive project, in this case, the boiler project. An argument can be made that use of means other than reserves to some extent for the boiler project is reasonable, as the replacement is not like kind, but is rather an improvement, and in this case, a significant improvement. In fact, use of reserves is often not an option due to this insufficient reserve balances. The reserve expenditures table notes the loan payments in the blue text as if the association were to repay the loan through reserves. However, this association could certainly fund the loan payments through means other than reserves, such as special assessments. So the resulting reserve funding plan identifies the loan proceeds, the money going in to the cash flow to fund the boiler project in 2022. That's in the bluish colored text. So we're continuing to note a 2030 as the critical year, and continue to note that the overall result is a greater amount of overall reserve contributions over time, with less burden on the owner fees to make up those contributions. Although this scenario is not quite as good as the scenario we just looked at, in part due to the interest paid on the loan, it still demonstrates a positive result from these energy cost savings. A quick note regarding the relationship between reserve balances, contributions, and expenditures. The blue line represents the reserve balance at an association over time. The low points in the cash flow or the minimum thresholds govern the contribution calculations, govern the annual reserve contribution calculations. In other words, those are the low points in the blue line as you move through time. The red negative bars indicate capital-intensive repair replacement expenditures. One of the biggest mistakes that we see is associations targeting the same reserve balance regardless of upcoming expenditures. We often receive comments like, we want to have $500,000 in the bank at all times, or we're doing really well as we have $1 million in reserves. When in fact, an appropriate reserve balance will vary greatly based on where you are at with respect to your large expenditures. Right before your big expenditures will require a large balance. Right after your large projects will allow for a lesser balance. I've been conducting reserve studies since 1999, and I cannot eyeball a reserve balance and know if it is high, low, or just right. Simply knowing a reserve balance does not mean much if you do not know the expenditures that the association is trying to fund with that balance, including these major mechanical system improvement projects. And with that concludes our presentation for today. Sam and I are willing to stay as long as you'd like to answer questions. Please enter those questions in the chat function. And we greatly appreciate your time today. Greatly appreciate you joining us today. As Matt mentioned, we'll send out via email not just the recording of this presentation, but also the slides to this presentation for your review at any time.
Thank you, Sam and Todd. One general question here about the timing of events. If we're looking at engaging in a reserve study, but we do not have an idea of these opportunities for improvement, should we be engaging with a firm like Alara first, or can we address some of these improvements after completion of the study?
Yeah, I'm going to give a little bit of a combination answer here. Ideally, yes, we would have an energy audit performed by a company like Alara, and the board would have reviewed that. They would have decided what they would like to do, what they would not like to do, so that we could implement that in their reserve study. However, moving forward with your reserve study prior to the energy audit, the energy analysis, it is also sufficient in that many of these projects will automatically include at least some level of upgrade. For example, replacement of vintage boilers. That reserve study provider will automatically include some level of upgrade because you can't replace them like kind. Same thing, garage exhaust systems. That reserve study provider will typically include, if you do not have carbon monoxide controls, controlling your exhaust fans, that reserve study provider will include that because that's the norm. That's what occurs. So there's a little bit of a combination there. It's going to depend on what type of projects you're considering. If it's a project like free cooling that Sam mentioned, that's not a typical project. So that would require some direction from the board and management as to whether we'd include that project or not.
Very good, thank you.
I agree with Todd on that. It would highly depend on the type of the project. But if there's flexibility with time, I think performing an energy audit or mechanical assessment prior to reserve study would be the safest way if budget allows. But the answer would change depending on project type.
Yeah, and sometimes the decisions as to which major mechanical system improvements to move forward depends on the results of the reserve study. What kind of funds are available to put towards these projects? So there is it can go either way.
Good. Sam, could you speak to the audience in general, the timeline of completing an energy audit? If they're looking at having a reserve study done, how far in advance should they be looking at getting that completed?
Sure. So typically for a high-rise residential building, I would say an energy audit would take approximately 5 to 6 weeks. And in that, so what we would do is we would basically perform a utility analysis, prepare a comprehensive energy audit report, and we would basically provide a prioritized list of recommendations. So in each project, feasibility, different options, energy savings, economics would be identified and provided. So Again, also depending on the project type, we would also include some information about phasing. So for instance, if the boiler plant is recommended for replacement, we would need to think about construction time, design time, and those need to be incorporated into the study as well, because central heating plant cannot be down during winter time because building needs cooling. So the construction needs to happen during summertime. So those are the things that we would need to look into depending on project type. But again, just to be on the safe side, I would recommend that audit be performed before or in conjunction with the reserve studies.
Very good, thank you. One last question here for Todd. How long is the reserve study good for? Should we update every 5 years or sooner?
Yeah, great question, great question. And we have attendees from all over the country on this call. So my comment is going to obviously not apply to those who live in a state that require reserve studies, as those states require specific intervals. Minnesota, Virginia, for example. Outside of the states that require specific intervals, an appropriate reserve study update interval, you're getting your reserve study up to date, will vary by the type of property. My opinion is from older, more complex properties, in other words, more dynamic properties, probably every 2 to 3 years is an appropriate time frame to get your reserve study up to date. Newer, less complex properties can probably get away with 3 to 5 year intervals to get that study up to date. But there may be some other factors. There may be major projects that you're getting closer to that you just want to make sure that your reserve funding is in alignment to be able to take on. That might impact the timing. An increase of major problems with a major component may impact that timing. So just in general, 2 to 3 years for older, more complex properties, and probably get away with 3 to 5 years for newer, less complex properties.
All right, very good, thank you. That is the last question we have here. So that concludes today's presentation. As mentioned earlier, we will be sending a recording of today's webinar as well as a copy of the handouts to each attendee. So be on the lookout for that in your email. Thanks for joining and have a great afternoon.